A new version of YOLO is out, and the big question is what is new? YOLO has always been known for real-time object detection, capable of identifying objects at 23 frames per second or more, but until now it has been limited to very small set of predefined categories which it needs to see during its training phase. And that has been a limiting factor because you cannot detect objects that the model has not seen during the training phase. And that's where the YOLO-E has stepped in and is trying to change the game, because it's now boasting that it can detect objects that it might not have seen during the training phase. And it is going through that process in three different modalities, either through text-based detection or image-based detection, or without any explicit input. So let's break down that what all that means. First, let's talk about the zero-shot inference. YOLO-E can now detect object which it has never explicitly trained to recognize. This is crucial because most object detection models do need to be trained on very specific data sets which are labeled, meaning they need to struggle with unseen objects. But YOLO-E is generalizing that completely, making it far more adaptable to real world scenarios, meaning it can recognize classes of objects it never seen before. This is fascinating. Imagine an agricultural drone flying over farmland and spotting signs of disease in crops. Even if it has never been trained on that specific kind of disease of the crops before, the drone can now identify that the crops are diseased in certain segments of the field, and then can help the farmers take quick action and prevent losses. Especially for automated farming, this is revolutionary. And then there is text prompted detection. The next level would be the text prompted detection. Here the model is given words like white hat, red hat, white car, sunglasses, mustache, tie, and it tries to find those objects in the image, just like Clip. You probably are familiar with Clip, where you can do a reverse image search just by words, and Clip goes and finds the similar images with the similar embeddings as the word that we are searching for. This is really powered by a variation of that called Rep RTA, which really fine-tunes how the model understands words without needing a huge language model. In fact, previously they had to encode those words by calling Clip or VIT, incorporating all those technology architecture of having the latent representation of the words and calculating the latent representation of the words in the model itself, so that it doesn't have to make those expensive, time-consuming calls to external large language models to have the latent representation sent back to them. So this could be used in digital asset management. Imagine a journalist searching an extensive media archive, and they can just simply type beach sunset or crowded street, and the system instantly retrieves the matching footage. So, and the next one is visual prompted detection, where a small red box highlights a reference object, say a red hat, and YOLO-E finds similar objects in the scene. So it has tremendous applications, especially in any kind of design or editing and photography. All of them are holding a sunflower, and you want to replace all the sunflowers by tulips. So you click one of the sunflowers and all the sunflowers would be selected at once, and then with one click you can replace all of them. There is a separate project that's also working on that, and we'll talk about that in a different video. But for now, that's one of the good use cases, that if you can detect one of the objects, you can detect all the similar objects in that scene. Even if it's a streaming data, you can do it in live. So for this feature, they use a separate architecture called semantic activated visual prompt encoder. So they use the visual prompts, which is in this case, let's say you are looking for a sunflower in a crowd, and it goes to the activation branch and looks for what neurons are activated. Then the semantic feature extraction branch extracts that and sees what similar neurons are activated in other areas of the image, and then selects those areas. This is done in a latent space, so this is very efficient and not very resource intensive. So as a use case, this is useful in industrial manufacturing. Say a factory worker marks a defective component in an image, and the system then methodically scans the entire assembly line for similar defects, and it can do that in real time. This is made possible by a new technology called LRPC, which really allows the model to detect new objects by learning broad general patterns. So let's quickly talk about LRPC. This is not something new, but this was there before. This is essentially region detection, and we talked about region detection in an earlier episodes, and I'll post the link for it. Region detection lies at the core of any kind of object detection model, because we first have to detect what region of the picture contains objects. So for example, if some part of the object contains cows and some part of the object contains grass and some part of the object contains fences, then we need to segregate those parts of the images and then see what kind of objects we're finding in each of those regions. Then so region detection is very important. So lazy region prompt contrast, this LRPC, is an evolution of that idea where the region is detected and then each region, now we need to extract what classes of objects are in that. So that lazy part is that lazily it classifies like cow. It throws out few different categories. It might be cow, it might be a horse, like we don't know, and then it fine tunes and figures out which are the most probable classes in that region. So that improves efficiency because it comes with as many possible classes as possible. Then imagine how we also perform as a human being, and when we look at an object from a distance, especially those optical illusion where you have an image looks like a horse from one direction and a cow from another direction, it's like that. So the lazy loading is the something like that. Assign as many classes as possible and slowly gradually refine it. It's slightly more complicated than that, but that's the basic idea. This could revolutionize autonomous exploration, especially on Mars, when a Mars rover needs to make autonomous decisions while doing its explorations and identifying rock formations and potential hazards, because the communication between Mars and Earth takes, even with at the speed of light, takes around 6.5 minutes. So that's too late before the Mars rover falls into a ditch. So it can do some autonomous driving already, but this will really change the landscape, figuratively speaking, when the Mars rover can actually identify objects that it might not have seen before. And why does this matter? Because in real world application, whether it's farming, media retrieval, manufacturing, or space exploration, we don't always have the luxury of a predefined list of objects. YOLO-E represents that major shift towards truly open world detection where models can identify anything, anytime, with or without specific guidance.